All right. If we're here, that probably means that we're in full cram mode for our Physics C test. So I'm just going to give you some quick tips on how to get all of the points possible on your AP Physics C free response. Because, of course, not all points are created equal, and we want to make sure that you're not leaving some easily gettable points on the board. So, just as an overview, this is for the pre 2025 test. The breakdown will be different next year. But right now it's 3 questions, 45 minutes. There's 45 points. They come in 3 sets of 15, so all free response questions are weighted equally. And approximate score for a 5. The cutoff for mechanics is somewhere around 60%, 55, 60%. Again, it depends on the exam curve on that given year. But if you're scoring in the 60 range, that's pretty safely a 5 most years. So, here's our first tip. If you see dry free body diagram, that should automatically be 3 points for you. So it is one of the first things we learn as physics students is how to draw a free body diagram, but it's also one of the most frequently tested for that reason, because we know students have familiarity with those. Drawing a free body or an extended body, which is the rotational version, has appeared on 9 out of the last 10 exams, and most of the points are just from drawing forces properly. An average of almost 4 of the 45 points are related to free bodies over the last 10 exams. So we can see here that with the exception of one of the sets last year, there's a decent number of points each year for free body diagrams. And we can see that there was a high of 7 back in 2021. And again, I just pulled the most recent exams. And the exam again did change in 2019. So, if you're drawing your free bodies, there are very specific ways you have to do it on the exam in order to earn credit. So we're going to go over that and show some good and bad examples. Very specific how you got to draw your free bodies. The language specifically states each force must be represented by a distinct arrow starting on and pointing away from the dot. So you can't draw vectors tip to tail, and you must draw the actual forces, not components. This is especially important on a ramp, where we rarely do analysis with the actual mg force, but we split it. Do not split on your free body diagram. So here's a full credit response on drawing the forces acting on an object on a ramp. This was actually on the exam like 2 years ago. It was only a couple points, but you just had to draw the forces acting on just an object as it slides down a frictionless ramp. And a correct response would look like this. So again, the weight force goes straight down. Earth's gravity goes straight down. Doesn't care that you're on a ramp or not. And normal force always goes out of the surface. So it meets that incline at a right angle. So that's a full credit response right there. Here's some various ways to not draw free bodies. Even if it helps you personally, do not put this on your exam on that portion or you'll not receive credit. So first, here's sort of our 4 rules. You can't draw vectors tip to tail. You can't have white space. So the arrows must actually touch the dot or else you won't get credit. Arrows should point away from the dot, and you can't show components on the diagram. Even if you draw the full force, do not draw components. So, tip to tail, even though this might be easier to look at for you if there's multiple forces, you have to draw them side by side. Also, you can't just have white space, so there's a gap there, not allowed. People typically don't do this one, but arrows should point away from the dot. And then you can't show components. So if I was doing that ramp example, I'd have to draw the mg straight down, not the mg sign down the ramp and mg cos into the ramp. It's about 50-50 split whether you're given a free body with a grid or not, although they've been a much bigger fan of grids in recent years. If you're given a grid, then that means that the relative lengths of your force vectors matter. So if there's any forces that balance, like mg and normal force on a flat surface, make sure that they're the same number of tick marks in order to show that. And if you're given a grid, think to yourself, there must be a reason why I am given a grid. If they didn't care about the lengths of the vectors, then they would not give you a grid in the first place. So there has to be a reason you're given the grid. Typically, this is some sort of comparison task where it has you draw a free body diagram at two different moments in time. So for example, if the second object that you're analyzing is twice as massive, your gravitational force should be twice as long. Or if you're increasing the separation of two objects by a factor of 2, the attractive force should go down by a factor of 4. So think ratios when dealing with these grid questions, if there's any known values there. And also, if an object is accelerating, make sure to show that the forces are not balanced. So if an object is accelerating to the right, there must be a net force to the right, so your rightward arrows must be longer than your leftward ones. Just as common as the free body is what we call extended body diagrams, which is when we have a non-point particle, so something that's rotating. This is the same thing, we just care where the forces are applied on our diagram. So the general rules are the same. You got to draw the forces from their point of application and point outwards. Can't draw vectors tip to tail, all that good stuff. And here's some reminders on point of application. Weight force is always through the center of mass, not through the center of the object, but the center of mass. So even if it's not uniform, you have to find where that center of mass is and draw your mg vector right down. Normal force always acts at the point of contact, and it always points perpendicular to the surface or the contact point. Any balancing force by a support can also be considered a normal force or a hinge force or an axial force, anything like that. It just has to point perpendicular, right? The word normal means perpendicular. Friction acts at the point of contact. Be careful about the direction. It is determined by the motion of an object, but a common tricky one here is that friction always points up an inclined plane for rolling objects. If it's sliding, not necessarily. But here's an example from 2018 where you had some sort of a wheel object going up a ramp, and you had to draw the forces, not components, acting on the wheel as it rolls up the inclined plane. So you had to draw the forces and at their correct position. So we got mg straight down, acting through the center of mass. And then we have two forces acting at the contact point. We have the normal force that's out of the surface and friction that's acting up the ramp. Our second tip is that best fit lines are a great way to fit in a few more points. So every exam in recent history has contained a best fit line section. And this is often independent of the other parts of the problem. College Board is much better about not double penalizing you. So you can typically attempt this part even if you do not know any of the underlying theory. And what they've done is they typically give you the model you're fitting to, although you may have to derive it. It kind of depends on the test. So it'll say, like, show that the maximum height as a function of launch velocity is given by this. And this means that sometimes you don't even need any physics knowledge to figure out what to graph and how to analyze the slope. And this averages 4.1 points over the last 10 years. And I took away the physics from this point. So these are the points from just best fitting, linear regression, solving for slope. None of the deriving points are even in this. So this is just pure data analysis points. So no physics knowledge is required for this. And you can see this one's a lot more consistent than the free body diagrams. It's typically about 4-ish points. You get a point for drawing a best fit line, you get a point for the slope, and you get 2 points for solving for the quantity of interest. So for plotting your points, if you're asked to plot points, which I haven't seen super recently, but still an important skill, try to use at least 75% of the grid space to avoid clutter. This has even been worth a point. You get, it was 2019, you got a point for using more than half the grid. And when drawing a best fit line, do not play connect the dots. It is not connect the dots. You're trying to get a best fit line, which means try and aim for half above and half below. And if you need help with that, use a ruler. You can bring one on exam day. A lot of people don't know that. Do not assume your line passes through the origin. If your trend line is making it trend towards a y-intercept that's not 0, yeah, it probably does not have a y-intercept of 0. Because also, the y-intercept has also been tested recently, and sometimes it does have real physical meaning that we wish to calculate. So calculating the slope of the best fit line, every single lab problem, you have to calculate the slope. The slope is typically not the end of the problem. It's typically equal to something else, and you have to do some algebraic manipulations with that. But in essence, it's always a slope two ways problem. So first, you got to find the slope explicitly using rise over run. Here it's important that you mark the points you're taking the slope between, and it should be points on the line, not the data point. I typically mark them with big X's, so just make sure it's clear to them where you're taking your slope from, because you can't just pick 2 data points. You have to pick points on the line. If you got data on the line, then that's cool though. You could also just get the equation of the best fit line using linear regression on your TI calculator if you put your data in the list and run linreg, but it's slower. Then lastly, you set your slope 2 ways equal to each other, and you can solve for what you want. So first, you have the slope of your model. So that existed before you even did an experiment. You'll have like slope equals, and then a bunch of constants. And then your second way is just slope equals this number that you found with the best fit line, doing rise over run or linear regression. Setting these expressions equal to one another will give you a solvable equation. And I typically say solve it symbolically first and just call slope its own variable, because that'll help you analyze some stuff later in the error analysis section. So here's a simple example. Suppose students are investigating how the moment of inertia I of a wooden plank depends on the distance d that it's pivoted from its center of mass. And they derive from the parallel axis theorem that the new moment of inertia is just equal to its moment through the center plus m times d squared. So the variables are, they're measuring I, the moment of inertia, as a function of d, how far away they pivot from the center point. So as such, first we'll draw a best fit line for this data. So here's their data. Again, they're measuring I as a function of d squared. And you don't have to get too fancy with the best fit line. Something that roughly catches half the points above and below. So mine's not totally perfect, but you can definitely see I attempted to get some points above and some points below the line. So our equation here is I equals md squared plus ICM, which is why we graphed I as a function of d squared. So I typically like to underline my variables so I know exactly what to graph. So what that means is that the slope of our line, which we're actually solving for, is going to give us the mass of the plank in this problem, because the mass is the slope. It's in front of the d squared. Because you can see that we're graphing a y equals mx plus b relationship. So this one is pretty simple because I can just explicitly find the slope and I'm done, because my quantity of interest actually is the slope. So slope in terms of symbols is m, and slope in terms of numbers is equal to rise over run. So you can see I drew myself a little slope triangle here. Roughly the points occur at 3, 3, and 10, 7. So I just do y2 minus y1 over x2 minus x1, and I get roughly 0.57 kilograms. Units matter. And then lastly, we could ask, what's the significance of the y-intercept of this graph? And here, notice that the y-intercept is the thing that's not changing in each trial, so ICM. and it's just the center of mass moment of inertia. So the y-intercept is just equal to the Planck's moment of inertia through its center of mass. And you can see from the graph it roughly crosses at 1.5 kilograms. A more complex example, this comes from 2023. This expression was derived earlier in the problem somewhere, where the period of a block of mass m attached to a set of n identical springs of constant k is given by this expression. T equals 2 pi square root m over nk. And suppose the slope of a graph of t squared versus 1 over n is called s. Derive an expression for the force constant of one spring using these quantities. So this is a very typical type example we'll see now, where we have to figure out what the slope is equal to in terms of variables, and then in terms of numbers, and then solve. So let's do that. So it says a graph of t squared versus 1 over n. So let's see what we can do to transform this into a t squared versus 1 over n relationship. So typically, if you got square roots, we want to just get rid of them by squaring, because it's easier to analyze that way. And if we got t squared, well, the only thing to do is square both sides. Then after simplifying, we get 4 pi squared m over nk on the other side. Highlighting our variables in red, we get t squared versus 1 over n is linear, as we expect. And just to be more explicit about it, we can divide by 1 over n. And we can see that dividing these two quantities gives us a constant value equal to our slope. So the slope of this line is equal to 4 pi squared m over k. So if the slope is equal to 4 pi squared m over k, that means ks is equal to 4 pi squared m. So k is just 4 pi squared m divided by the slope. And you would typically compute the slope as a number here and do it explicitly, but we just did it symbolically here. This is a must-know skill. Third tip, if you see a function, you got to do calculus with it. That's all there is to it usually. They wouldn't give you a function if you don't have to do calculus with it. If you're given a continuous function, not a data table, a continuous function or graph, you're almost guaranteed to have to use calculus with it. So the first thing you should do when you're given a function, like force as a function of x, force as a function of t, v of t, a of t, x of t, whatever, see what calculus you can see with it on your formula sheet if you can't remember. The calculus involved, however, is usually quite simple. They typically don't go beyond basic power rule or chain rule with trig functions. And sometimes you don't even need to know how to do the calculus. You can just write the expression down and type it into your calculator. And the C in calculus is definitely a proper name. At least 5 points on the last 10 exams are typically calculus related. So this, of course, integrates calculus and physics together, so there are quite a bit of points here. But some of these are just from basic power rule derivatives and integrals. So we saw we had quite a binary year with 2023. The first set had 3 calculus points, but the second set had 10. But that's kind of all spread out. But notice it's never 1 point. So it's important to understand these routines. And if you're given a function, you're going to ask, should I take a derivative or should I integrate? Well, just going back to definitions, derivative is all about rate of change. So if you're trying to figure out how fast the thing you're given is changing, you got to take a derivative. One thing about the derivative is it is local. The derivative is happening at one spot. So you're probably not going to calculate the derivative between 2 time periods. You're going to want the rate of change of force at this time. And again, if you're given a graph, that's represented by the slope of the tangent line. So the integral is not just the area under the curve. That's kind of a bad way of thinking about an integral in general. What an integral is it's a big summation of a bunch of things. So if you're interested in seeing what happens after you add up a bunch of stuff, that's your indicator that an integral is involved. Anytime there's between or some sort of an interval, it is probably integration. Especially if there's any notion of chopping something up into a bunch of pieces and adding them together, like moment of inertia or center of mass. If you're given a graph, though, then it is just the signed area between the function and the axis. So here's a differentiation example from last year. Here's where a lot of those calc points came from. So you're given a velocity time function of a cart, and you wanted the magnitude of the maximum force delivered to cart A during the collision. So first thing we do is we scan our formula sheets for some calculus relationships that we could utilize. And that's going to be our basic F equals ma, and acceleration is just the rate of change of velocity. So that means that I can find A by differentiating the velocity function, and then I can find force by multiplying by the mass, and then either by setting the derivative equal to 0 and and plugging in, or just by graphing and finding the maximum. You can see the maximum occurs at 12,000 newtons in the negative direction. Now for an integration example, here you're given the force on a cart as a function of time, and you want to figure out the net impulse acting on the cart. And the key that this is integration is, well, we're given a graph, and the collision doesn't just happen at one time, it happens over this whole interval. So we're going to have some sort of integral. To figure out what exactly we're integrating, we can look at our relevant equation. Scanning the physics C formula sheet, we get the relationship that impulse is the time integral of the force function, which is also the change in momentum. So I just wanted impulse. So I just integrate the force function from the starting point to the ending point, which is basically between the zeros. And either take the antiderivative by hand, or at this stage you could just type it into your calculator, and we get negative 2.03 Newton seconds of impulse. And again, make sure your units work out with this. If force is in newtons and t is in seconds, well, impulse is going to be those newtons in seconds multiplied together. All right. There have been a lot of graph construction questions in recent years, and a lot of them are qualitative. So it's almost certain that you're going to be asked to qualitatively graph how a quantity changes over time. And the solution to these are likely not derive the formula and then graph it. It's likely a think about it and sketch the general behavior thing. And the best way of doing this is thinking about the extremes of the interval to get your endpoints, and then start thinking about a connector. And these are typically about 3 or 4 points. So you can see they've really been increasing in recent years on the amount of points related to graphs that you make. So there's been a lot in recent years. So all the low values are from the older style tests. So graphing is a very big thing this year. And this isn't best fit line. This is some sort of relationship that you have to graph. So I call this ask before you graph. Where should my graph begin? Is it positive, negative, or 0? Where should my graph end? Positive, negative, or 0? And then think what should connect these points. Is it a line? Is it a concave up curve? Is it a concave down curve? Something else? Something that peaks and falls? And then if it is quantitative, you don't have to worry about the scaling as much, but explicitly label. Do you know that max value? Do you know when it hits 0? Do you know where the inflection point is? Those things. So here's a good one that I liked recently. So we have a rod that's initially horizontal, and then it is released and swings downwards towards a vertical position, speeding up. And we want to graph the torque acting on the rod about this pivot point and its angular velocity as a function of time. And we are stopping it right when it's about to hit the building. So right when it's vertical, basically. So here's our solution. So first, let's think about the torque graph. The torque is maximized at the start since the gravitational force is totally perpendicular to the rod at that point. So you're getting maximum torque. And then at the end, the rod is not at all perpendicular to gravity. So there's no torque at the end. And I know a concave down curve should connect these points. The rod starts at rest, so omega should start at 0. Again, that's an easy one, right? If the rod starts at rest, you shouldn't have any angular velocity. And when the rod hits the bottom, it should be at a very high angular velocity. And since the torque is decreasing, that means that your omega graph should also be concave down. And if either of these were tricky, you just needed to actually get one of these to solve for the other, because the torque graph is roughly the derivative of the omega graph. So here's our solution. So the torque, you start with a maximum torque, and then as the bar swings, less of gravity is perpendicular, so it slowly decays towards 0. And since torque can be thought of as the slope of the omega graph, that means that we have a large positive slope at the start, and then it slowly shallows out. So again, it's gaining speed the whole way, but the rate at which you're gaining speed is decreasing. This is a tricky example, but I wanted to show it because it can show you the thinking skills we need for that. This is probably the best tip if you're just trying to get partial credit and if you're totally stuck. If you don't know what to do, just write something that's true. It's pretty common that if you know what you're doing in the class overall and you're stumped on a specific problem, you can probably at least identify what topic it is. Is it a collision problem? Then momentum's probably involved. Is there a ramp involved? There's probably energy. Is it rolling? Then there's rotation. Do you see the word circle anywhere? Then centripetal force probably shows up. And once you identify the relevant principle, you should write some sort of equation related to that, and that can typically even get you a point, even if you have no idea how to finish. So for example, if it's a collision, I can write momentum before equals momentum after. Is it going down a ramp? Well, you can write potential plus kinetic equals potential plus kinetic. Are you rolling without slipping? The no slip condition is almost always worth a point if you write that somewhere. Are you in a circle? Well, if you're in a circle, you're guaranteed to have to use F equals mv squared over r at some point. So these are ways to get little points that will start to add up. And your little bonus tip, attempt all the parts. Even within each question, many of the parts are completely independent. Do not think that just because you don't get part A, you can't get part B. They design it to be as independent as possible so that you're not penalized for missing a minor thing along the way. So I'd recommend just kind of reading through everything first. And even if the parts are still interdependent, still cite any physics principle you think applies, or make up an answer to the previous part and saying, assuming the answer was this, I would do these steps. If you don't know what to do, write something true. You will probably get partial credit. And additionally, there are many conceptual short answer questions, checkbox style, that are typically like increase, decrease, stay the same, that you can justify. And those are a quick way to get a point or two. And you can typically just justify those in a quick sentence. So in conclusion, the best tip for acing the AP exam is, of course, knowing the content. So practice is going to get you exposure to all of that. But again, if you do enough of these exams and pass papers, you really get to see the patterns. So by doing these exams, you see the patterns, you see how they ask questions, and you'll notice the common themes of the questions. But hopefully this gives you some tips to sort of send you over that next score boundary you're looking for. Because if you add up all the little tips we did today, it can certainly take you from a 4 to a 5 if you answer all those questions. Those are just some things to focus on.